Good morning, everyone. My name is Basmala, and today I'll be presenting my research on enhancing microbial fuel cells using agriculture residues and the challenges we have faced and lessons learned from our experiments. This work was done under the Talaria program with the guidance of my mentor, Angela Leon. So, what are microbial fuel cells, or MFCS? Microbial fuel cells are bioelectrochemical systems that use bacteria to generate electricity. The bacteria consume organic waste, releasing electrons, which we capture as energy. This process not only produces renewable electricity, but also treats wastewater at the same time. So, microbial fuel cells give us a dual benefit: clean energy and sanitation. And in Egypt alone, about 35 to 45 million tons of agricultural residues are generated every year, which, with rice and corn straw making up the largest share. Most of this waste is burned or dumped, creating significant pollution. At the same time, Egypt faces energy shortage, such as power cuts, while other countries like Kenya and Namibia struggle with low rural energy access. This creates a clear opportunity to turn waste into resource. Looking at the literature review, performance from single substrate is quite limited. For example, constructed wetland microbial fuel cells reached about 388 millivolts. Dairy wastewater gave around 360 to 460 millivolts. So the common bottlenecks across these studies are low surface area electrodes and weak microbial activity. So improvements in materials and design are needed. The aim of my study was threefold. First, to improve performance using combined agriculture residues. Second, to investigate design and operational challenges. And third, to extract lessons that could guide future applications of this technology. So, let me tell you about our two-phase experiment. Firstly, we carried out the study in two phases. In phase 1, we begin with a simple microbial fuel cell setup. The electrodes were modified with activated carbon from rice and corn straw, activated at a ratio 1:1 pi char to KH. This gave us a power density of 226 milliwatts per square meter. In phase 2, we enhanced the strategy. We optimized the activation ratio to 1:3 and also added nanomaterials derived from sea leaves. This approach was far more effective, significantly improving microbial attachment and resulting in a power density of 390 milliwatts per square meter. Here is our pie chart when we get it from our tubular furnace after pyrolysis, and here is our first experiment and our second experiment. Here, I compared my results with a study by Jayo and colleagues from 2020, while their electrodes used activated carbon from rice husk, mine combined rice straw, corn straw, and sea leaf nanomaterial. Their system reached a surface power density of 317 milliwatts per square meter. In contrast, my experiment achieved 390 milliwatts per square meter, about a 22% improvement, thanks to the multi-source and nano-enhanced carbon. However, there were clear engineering challenges. The electrode coating was sometimes uneven when mixing carbon and C nanomaterials. The total reactor increased the electrode spacing, which lowered power density because resistance had increased because the spacing between two electrodes also increased, and reproducibility was an issue since electrode fabrication was not always constant. Operationally, the system was very sensitive to environmental factors like temperature, pH, and substrate levels. We also lacked inside sensors, so it was difficult to track real-time changes. And finally, with no maintenance during the experiments, biofilm build-up increased resistance and reduced performance. And there were also economic limits we have mentioned in our paper. Materials like KOH and nanomaterials are relatively costly. Fabrication was done manually, which was labor intensive, and scaling up this method in rural areas remains a major challenge. From all of this, there are several key lessons we have to learn. First, mixed residues are improved performance, reaching 0.55 volts and 390 milliwatts per square meter. Second, electrode spacing is critical for efficiency. Third, a stable environment is essential for a constant output. Regular maintenance, also like cleaning and servicing, is also necessary. And finally, using local residues lower costs and improve stability. Based on this lesson, I recommend the following. Use integrated biomass source like rice and corn and sea. optimize electrode spacing and geometry and insulation for better temperature control, and standardized fabrication and maintenance protocols, and prioritize local biomass sourcing to reduce costs and improve sustainability. These steps can also expand the use of microbial fuel cells as environmental sensors. In conclusion, microbial fuel cells can transform waste into energy while treating wastewater. My study shows that mixed biomass and design improvements increase performance, but the systems are still limited by cost, predictability, and environmental sensitivity. With further development, however, MFCS have real potential for decentralized energy production and real-time sensing, and also contributing to the UN Sustainable Development Goals and rural sustainability. I'd like to sincerely thank the Talaria program for this opportunity, and especially my mentor, Angela Leon, for her guidance and support throughout this project. And thank you very much for listening, and I look forward to hearing questions you want to ask me.